Hello everyone, and thank you for joining me today in our lesson about function transformations. We have two objectives today. We are going to identify the transformations caused to a function by looking at the function rule, and then we will sketch some transformed functions based on those function rules. Now in class we would do a little bit of a discovery activity to kind of see how these transformations play out. We're going to do just a brief version of it here. So if we consider the absolute value function shown as the parent function for this demonstration, let's see what happens when we apply different operations to it. For example, if we subtract 2 inside of those absolute value symbols, notice the graph shifts or translates to the right 2 units. The green one is a translation of the red dotted one to the right 2 units. But what about if we add 2 inside those absolute value symbols? Well, now the graph actually shifts to the left 2, translates left 2, which is what the opposite of what you might think. But when that addition and subtraction is applied directly to that input variable x, the graph moves in the opposite direction to kind of balance that out. What used to happen at 0 now happens at -2 for this blue example. Okay, what if we add or subtract outside of those absolute value symbols? Well, if we subtract 2, the graph translates down 2, which is maybe what you might expect. If we add 2, the graph translates up 2. So when we add or subtract outside of those absolute value symbols, the graph moves in the direction that maybe we would expect. What if we multiply? Well, here let's multiply by 2 just as an example. Compare the black graph to the original red one. The black one seems to have a steeper slope. The word we would use there is a vertical stretch, specifically by a factor of 2. All of the y values of the original have doubled, stretching that graph, making it look steeper, increasing the slope, I guess. What if we multiply by a fraction like 1/2? Well, now the graph has shrunk. This is a vertical shrink. The y values have been cut in half here, giving us this vertical shrink on the graph. Finally, what if we multiply by a negative? Well, now we get what we call a reflection. The y values have now become their opposites, and so reflecting those points across the x-axis. The graph used to pass through, 5, 5. Now it passes through 5, -5, because the y values have become their opposites. So if we take all of those ideas and kind of summarize them, you could take a look at the table on the right-hand side. And you could write this down or take a picture of it, whatever you want to do. When we add or subtract inside of the grouping symbols of a function, like absolute value symbols, that causes a horizontal translation. Right for subtraction, left for addition. When we add or subtract outside the grouping symbols for a function, the graph translates the way you might expect. Down for subtraction, up for addition. When we multiply by a factor in front of a function, we cause either a stretch or a shrink. A stretch if that multiplier is bigger than 1. A shrink if that multiplier is between 0 and 1, like 1/2. And finally, if that multiplier is a negative, we will cause a reflection across the x-axis. So let's practice with those ideas a little bit. Here on the screen, we've got the graph of some generic function, just a little slice of one. But we're going to use it to practice with these transformations. So on the left-hand side, we've got 3 different transformations of f of x. We'll identify what's happening first, and then we'll go ahead and actually sketch that transformed version. So let's start here with f of x plus 3. I noticed that plus 3 is taking place outside of the parentheses, and so if we follow the rules we wrote down on the last slide, this is going to translate our graph up 3. So to sketch that, I'll come over here now, and I'll take each of these points and move them up 3 units. Every red point on that original graph gets moved up 3 units. Here is f of x plus 3. In green, f of x minus 1. I see that minus 1 taking place inside parentheses. So from our last slide, that will cause a horizontal translation, specifically to the right 1 unit. So we take every point on this red graph, and we shift to the right 1 unit. Here is that sketch. Down in purple, 2 times f of x. Well, from the previous slide, when we multiply, that's going to cause either a stretch or a shrink. Here, 2 is bigger than 1, so we're going to double all the y values. That's going to cause a vertical stretch here, specifically a stretch by a factor of 2. So let's take all of the y values on the original red graph and let's stretch them by a factor of 2. Let's double them. For instance, this first point has a y value of 1. Let's double that. If you double 1, that turns into 2. This next point has a y value of 0. Well, if you take 0 times 2, you still get 0. These 2 points have a y value of 2. When we double those, they turn into 4. So we'll be up here at 4 and 4. And we'll go ahead and give this a sketch here. Oops, too far. There we go. This would be a good time for you to pause and practice perhaps. So if you would consider pausing the video, maybe giving these ones a try, I'll put the answers on the screen here in just a moment. Let's start with f of x minus 4. That minus 4 takes place outside of the grouping symbols. That causes a vertical translation, specifically down 4 in this case. So we'll take every point on this red graph, shift those y values down 4. Notice that the shape of the graph doesn't change, just its location does. And that's what a translation does. It moves it to a new home on the coordinate plane. F of x plus 3. That plus 3 inside the grouping symbols tells me it's a horizontal shift, specifically left 3 in this case. So we'll take every point on this red graph and shift it to the left 3. Again, notice that the shape of the graph doesn't change, just its location on the coordinate plane. Now here's a case where we've got 2 transformations happening. I see a multiplier by 1/2, and that's going to take our graph and shrink by a factor of 1/2. But then also there's a negative in front, and that's going to cause our graph to reflect across the x-axis. And I'm definitely not writing incomplete sentences here. Okay. Well, we can either reflect and then shrink or shrink and then reflect. With those two, the order doesn't really matter. I think I will shrink and then reflect, I suppose. So consider this point right here. It's got a y value of 1. If we take 1 and multiply it by 1/2, we'll get 1/2. But then we have to reflect that point across the x-axis here. So that's going to end up down here at negative 1/2. This point has a y-coordinate of 0. If I multiply that by 1/2, I still get 0. And since it's on the x-axis, I can't reflect it across the x-axis because it's on the x-axis. These 2 points have y-coordinates of 2. If we cut those in half, multiply them by 1/2, they'll turn into 1. But then remember, we've got to reflect those across the x-axis down here to negative 1. Notice that when we shrink or stretch, we do change the overall appearance of the graph, not just its location on the coordinate plane like with a translation. Now, those examples were all well and good. However, we kind of did one transformation at a time. We need to be able to handle multiple transformations and know in which order to apply them. So consider this here, same graph f of x, but now if you count the number of transformations we have, I see 1, 2, 3, and 4 happening here. The key is that we do them in the correct order. There's kind of an order of operations for this. Okay, now I'm going to write that down actually up above here. When we have multiple transformations to apply, the first we have to do is any horizontal translation. That's the stuff inside the parentheses, which we're kind of used to with an order of operations, right? Parentheses come first, grouping symbols first. Okay, after that, we need to do, and the order of these doesn't really matter, we need to do any stretching, any shrinking, any reflecting. That's caused by a multiplier in front of our function, remember? And then finally, we will do any vertical translating. It really follows the order of operations that we typically do for, say, evaluating expressions. So if I apply that process to what we have going on here, I start with any horizontal translations, and so I'll number them here. It looks like we're going to shift to the left 1, okay? I'm not going to try to color code here. It might get a little bit too fancy. In front here, it looks like we have to stretch by a factor of 2 and then reflect across the x-axis. And the order in which we do that doesn't matter. But in the grand scheme of things, this 1, 2, 3 order does. Our last translation here will be a translation down 3. Now, if you can handle all of those at once, that's cool. That's what I'm going to try. If it helps you to first shift everything left 1, sketch it, then stretch everything, sketch it, then reflect everything, sketch it, then shift down 3, sketch it, that's cool too. It's whatever works best for you. I'm going to try to do all of this at once here as best I can. Okay, and we'll start with this point right here. We're going to take a left 1, stretch by a factor of 2, reflect, and shift it down 3. Okay, here goes. If we go left 1, we'll be over here. Now we've got to stretch that by a factor of 2. So we've got to double that y value. That's a y value of 1, and when we double it, it'll move up to 2. Now we've got to reflect that across the x-axis, down here. And then remember, our last step is to shift everything down 3. So from there, we'll go down 1, 2, 3. That first point, I'll circle it one time. There's our transformed version of it. Okay, I'll try to go a little bit faster going forward. Again, left 1, stretch by 2, reflect and shift down 3. So here goes. Left 1. If I stretch that by a factor of 2, it doesn't move because it's got a y value of 0. If I try to reflect it, it doesn't move because it's got a y value of 0. But now we've got to finish by shifting down 3. All right. Moving on here, we go left 1. Got to double that y value, stretch it by a factor of 2. Now reflect across the x-axis. We were up at 4, now we're down at negative 4. And let's see, then we have to, what, shift down 3. So 1, 2, we go all the way off, down to negative 7, I suppose. Okay, now if you can track all of that in your head, maybe you can do this last point a little bit faster. Remember where it is relative to the one we just did. It's 2 units away from that one. So if I can imagine what's going to happen in my head, it's going to be 2 units away from the one we just did. And if that didn't make a ton of sense, don't worry about it. Go through all the motions of applying those transformations in order. But that's just a shortcut we might be able to take eventually. Especially when we start memorizing what some of our parent graphs look like. That's kind of the whole power behind this stuff after all. So when you have multiple transformations to apply, there is an order to it. You can see the order there. Let's finish up with a little bit of a challenge. We've got this function f of x. Consider that the parent function. There's a transformed version in blue. We have to write the rule for the transformed version, basically doing what we just did in reverse. Okay, now let's look for, our order of transformations here. Let's first check to see if there's any horizontal shifting. Well, if I take this landmark point on the red graph and compare it to, its same landmark spot on the transformed graph, it would appear that there is a shift to the left 3. So I have to construct my function in such a way that there is a shift to the left 3. And I can make that happen by adding 3 inside of this function's grouping symbols. Okay, now let's look for any stretching and reflecting. This red graph appears to be reflected across the x-axis, so I know there's going to be a negative in front here, but is there any sort of stretching or shrinking? Well, let's compare. These two had y values of 1. These two appear to have y values of 1/2. Negative 1/2, I guess. So I think there might be a shrink by a factor of half, but let's confirm that by looking at some more. These have a y value of 4. These have a y value of negative 2. So they've been reflected and also shrunk by half. 2 is half of 4. So it would appear that there's also a shrink of 1/2 happening here. In terms of vertical translations, I don't see any shifting up or down. This y value matches here. Okay, I don't see the location of that vertex is still on the x-axis there, so I don't see any vertical shifting, no vertical translating at all. So here we have it, negative 1/2 times f of x plus 3. Today, we learned about function transformation rules. We practiced applying them to a generic function to get that practice that we need. That is all for me today. Thank you for watching.